to start chapter 18. It is quite a hefty chapter, I will tell you. It's a lot. I think I don't know how many slides I have here, but it's a really, really big topic. So I want to make sure we have about a month left, I think, and the entire month is going to be spent on this, this unit. So it's all about chemical equilibrium. What I'm going to do today is just talk about what it looks like what is it and what can we do with it. So the first thing about chemical equilibrium is that it only applies to reversible reactions. So a reversible reaction is a reaction where the products can react to reform the reactants. And we're going to be using a double arrow because the word equilibrium usually implies that you have two opposite processes that are occurring at the same rate, right? So for example, way back when we studied the states of matter and we looked at changing state like melting and freezing. Melting and freezing are two opposing reactions, or opposite. So melting is from a solid to a liquid and freezing is liquid to a solid, right? So if you have a system at equilibrium, say you have ice water at 0 degrees and you can hold that temperature steady at 0 degrees, ice melts at 0, it also freezes at 0. So you can have equilibrium. It just means that there's opposite, what do you call it? Opposite processes. Oh, I can't find my, hold on. I moved the bar, so now I can't find my mouse. There we go. I gotta let O into the class. So in order to be able to have two opposite processes occurring at the same rate, you obviously have to have a reversible reaction. You can't have equilibrium for a reaction that only proceeds in one direction. So let's look at an example. Mercury 2 oxide decomposes when it's heated. So the overall equation is 2 mercury 2 oxide as a solid will decompose into 2 mercury atoms plus oxygen gas. But mercury and oxygen can combine to form mercury 2 oxide when heated gently. So mercury 2 oxide decomposes when heated, but mercury and oxygen can combine to form mercury 2 oxide at the same time. So we have the reverse reaction occurring. Suppose we heat mercury oxide in a closed container so that the oxygen gas cannot escape. Once the decomposition begins, the mercury and oxygen that's released can recombine to form HGO again. So both reactions happen at the same time. The rate of composition, meaning mercury and oxygen combining to form mercury oxide, will eventually equal the rate of decomposition. This would be equilibrium. Mercury and oxygen will combine at the same rate that mercury 2 oxide decomposes. At equilibrium, as long as conditions remain the same, the amounts of mercury 2 oxide, mercury, and oxygen will remain constant. If both reactions are occurring at the same rate, at equilibrium, as long as nothing changes, so temperature doesn't change, pressure doesn't change, volume doesn't change, nothing changes, you don't add anything or take anything out, then the concentration of your reactants in your products will remain constant. At this point, a state of dynamic equilibrium has been reached between the two reactions. So there is no net change in the composition of the system. Okay, as long as it's in a closed system, that's number one. Because an open system, if you have either gaseous reactants or gaseous products, they will be allowed to escape. So you have to make sure the system is closed and that all of the conditions stay the same. A reversible reaction is in chemical equilibrium when the rate of its forward reaction equals the rate of its reverse reaction and the concentrations of everything in the reaction remain unchanged. It does not mean that and I want to make sure that this is clear, equilibrium does not mean that the concentration of the reactants equals the concentration of the products. It can, but it doesn't necessarily have to hold true. It is about the rate, the rate of the forward reaction equals the rate of reverse. That is equilibrium. The equation for chemical equilibrium is written using double arrows. So you see here. In some cases, the forward reaction is almost done before the rate of the reverse reaction is high enough for equilibrium. So in this case, the products of the forward reaction are favored at equilibrium. There is a higher concentration of products than reactants. In this case, you would use a longer arrow for the forward reaction and a smaller arrow for the reverse reaction. So again, if the forward reaction is almost complete before the reverse reaction before the reverse reaction reaches equilibrium, that means the forward reaction is favored. In other cases, the reverse reaction is favored. So at equilibrium, there will be more reactants than products. This is why I said it's really important that you understand that equilibrium does not mean that the concentration of the reactants equals the concentration of the products. It's about the rate of reaction. Now, using the different size arrows doesn't mean that one reaction happens more than the other one. It just gives you an indication of which direction is favored. So in this case, the forward reaction, what was it again? The forward reaction is almost finished. So as the reaction proceeds, the forward reaction occurs almost to completion before equilibrium is reached. In this example, the reverse reaction is favored. Okay, and that has to do with, it could be the strength of the reactants over here. So for example, bringing it back to acids and bases, because this is an acid. Carbonic acid is a weak acid. And I know this is going to be like, oh my God, I don't remember any of this. H2CO3 is a weak acid. How do I know? Double arrows, remember? It's a weak acid, which means it's conjugate. So what's left over after it donates the proton is bicarbonate, which means bicarbonate is a stronger acid. So it's going to proceed mostly in the reverse direction. So you'd use a larger arrow for the reverse. Sometimes forward and reverse happen almost the same amount before equilibrium is reached, and then you would use an equal double arrow. I will not expect you to write your equations using longer or shorter arrows, depending on which reaction is favored, because most of the time you're not going to know which direction is favored. So we just always write it with the equal double arrow. Okay, so we're going to get to something called the equilibrium expression. We're going to go through it using a generic example. Two substances, A and B, react to make the products C and D. C and D can then react to remake A and B. Oops, backwards. Come on. So I'm going to use N, M, X, and Y for coefficients, because in the equilibrium expression, they're going to be raised to the power of their coefficients. So they each get their own. This is the overall reaction that you would write. Oh, lost my Bluetooth. Okay. Okay, why is the laser there? Anyway, at first, so looking at the graph, I really love this graph as a way to show how equilibrium occurs. So we have the forward reaction here and the reverse reaction on the bottom. For the forward reaction, you have the forward reaction starts to decrease in reaction rate because the reverse reaction starts to increase. So as the forward reaction proceeds, you're using up A and B, and as you use up A and B, the rate, this is the reaction rate on the y-axis, the rate of forward is going to decrease as you use up your reactants. As you produce, like at the beginning, you see how the reverse reaction starts at 0, because at the beginning, when you first start the reaction, the reverse reaction literally cannot occur because you have no products, right? At the very, very beginning, as soon as you mix A and B, there are no C and D, not until the forward reaction starts. And as soon as it starts, you start to use up reactants, which means your reaction rate decreases. At the very beginning for your reverse reaction, you have 0 products, but as soon as the reaction starts and you start producing products, those products can start to form the reactants, which means your reverse reaction is going to start to increase as you start to produce more C and D. Eventually you get to a point where the forward reaction rate equals a reverse reaction rate. And as long as the conditions remain the same, it will remain at equilibrium. And that's where the forward rate equals the reverse rate. So at the beginning, the concentrations of C and D are 0, which is why the reaction rate starts here. The concentrations of A and B are at their maximum at the beginning of the reaction. Over time, the rate of the forward reaction decreases because A and B are being consumed during the reaction. And after the initial reaction starts, the concentrations of C and D are going to increase, which means the rate of the reverse reaction will increase. When the two reaction rates become equal, that is where equilibrium is established. We do call it dynamic equilibrium, meaning it can change. Because if you do anything to disrupt the system, which is the next section I'll talk about on Wednesday. Yeah, Wednesday. If you change any condition in the system, you're going to disrupt equilibrium, and you can reform a new equilibrium with different concentrations depending on what the stress is, and that's what we'll talk about on Wednesday. So at equilibrium, the concentrations of A, B, C, and D don't change as long as conditions stay the same. After equilibrium, the concentrations of products and reactants remain constant, so the ratio of their concentrations should also stay the same. This is when we start manipulating ideas into forming a math equation, or a formula rather. So the ratio of the product C to the X times D to the Y to the product A to the N times B to the N, M, sorry, for this reaction has a definite value at a given temperature. The definite value is the equilibrium constant of the reaction, and it's given the letter K. Now, the reason why this, here, so this is your equilibrium expression. It is products over reactants. Concentrations are all in moles per liter, molarity, so that's why we use the square brackets. Each of the species, whether it's a product or a reactant, is raised to the power of its coefficient, which accounts for the ratios of reactants and products, the mole ratios between all of them. And the reason why this chapter is so meaty, why it has like so much stuff in it, is because there's a lot of different values of K. Now, back in the acid base chapters, I talked about Kw, which is the ionization constant of water. Ionization constant of water. Does anybody remember what Kw was? I'll just go ahead. Does anybody remember what Kw we did during the acid and base? No, okay. No. Yeah, I was like, I'm just gonna assume nobody remembers. Okay, so put this on pause for a second, just to show you what I mean by It's products over reactants. So for the ionization of water, you got 2 moles of liquid water, which, oops, no brackets yet, which form hydronium, which is aqueous, and hydroxide, which is aqueous. Now, the thing about writing an equilibrium expression, you can only include compounds or substances. I'll use substances. You can only include substances where the concentration can change. So the 2 states that are included in equilibrium expressions are aqueous and gas. That's it. Because you can't change the concentration of a liquid, you can't change the concentration of a solid. So if I was writing an equilibrium expression for this reaction, I would ignore the liquid water because you can't change the concentration of the liquid. And so you look at what we're doing, what we're trying to study is the concentration, which is represented by the square bracket, at equilibrium. And if we change the conditions, we change equilibrium, which means the concentrations can change, but not for liquids and solids. So here we would have Kw is equal to the concentration of hydronium, and this is balanced. So our coefficient is 1, which means it's to the power 1, times hydroxide, also raised to the power of 1 because there's no coefficient there. So that's the products. Now, normally you would say over H2O squared because there's a 2 here. But it's a liquid, which means the concentration can't change, which means it's always going to be 1, which means you can basically ignore it. So this is how we got in the chapter, what was it? Chapter 15, 15 or 16? No, 15, on titration and pH, when we started doing the logarithms and all that kind of stuff. This is how I started. And when we measure pure water, we measure the conductivity. We find it as 1.0 times 10 to the minus 14 molar squared. Does that sound familiar? It should sound familiar because that was the basis on calculating hydroxide and hydronium concentrations in acids and bases. And then we use the logarithm of the concentrations to find pH and pOH. This all stems from equilibrium chemistry. Okay, so that's where that comes from, is this products over reactants raised to the power of their coefficients, but it only applies to aqueous and gaseous substances because those are the only substances whose concentrations can change, right? For an aqueous solution, we can add more solute and make it more concentrated. We can take out solute and make it less concentrated. A gas, we can shove more particles in the same volume and make it more highly concentrated, or we can take molecules out of the same volume and make it less concentrated. There is no way to make liquids and solids change concentration. They're pure substances. Like, how do you make water more concentrated? You can't. You could say, well, let's add some sugar. Well, then it's no longer a liquid, it's a solution, right? So liquids and solids are left out of equilibrium expressions. Okay. The concentrations of the products in a chemical reaction appear in the numerator, and each concentration is raised to the power of the coefficient. So this is very different from reaction rate, which we did in the last chapter, where you have to use experimental data to calculate the exponent or the order of the reaction. Now it's really easy. You have a balanced equation. If you don't, balance it first, and then you use the coefficients, and that is the exponent. So these are the products of the forward reaction. The reactants are in the denominator, again raised to the power of their coefficient. So they're the reactants of the forward reaction. K is independent of the original concentrations, which makes sense because the original concentrations of the products would be 0. But it is dependent on temperature because, again, temperature is a condition that can change reaction rate. If you change reaction rate, which is what we studied in the last chapter, then you're going to disturb equilibrium. So the value of K for a particular equilibrium system is found experimentally. Chemists analyze the equilibrium mixture and determine the concentrations of all substances. The value of K for a given reaction at a given temperature shows the degree to which the reactants are converted into products. If K is equal to 1, that means that the products of the concentrations, okay, this is sounding really super complicated and mathy. If we just do this, products over reactants. So if this is equal to 1, that means at equilibrium, the concentration of the products equals the concentrations of the reactants. Okay, equal concentrations, products and reactants. If K is low, again, remember products over reactants, square brackets. That means that the numerator is higher than the denominator. That means that the forward reactions happen before equilibrium and reactants are favored. Oh, sorry. Yeah, if K is low, Monday morning, bro. If K is low, it means that your denominator is a larger number, which means the forward reaction happens before equilibrium and the reactants are favored because that means you've got a high number, low number over a high number. That tells you the forward reaction is favored because you're producing, the reverse reaction is favored because reactants are higher. So you go more backwards. Okay, so if K is high, then that means that your numerator or your products is high, which means your forward reaction is favored because you have a higher concentration of products when equilibrium is reached. So let me just say this again, because I feel like I might have confused everybody. If K equals 1, that means at equilibrium, because remember K is at equilibrium, the concentrations of reactants and products are equal. I would say this barely happens, but just if it's 1, then you know that the forward and reverse reaction occurred at the same, in the same amount. So neither direction is favored. If K is low, the forward reactions were favored before equilibrium. Sorry, I just did it again. Oh, I think it's the way that I worded this. I got to go back and change this. The reactants are more, which means the reverse reaction is favored because you have reactants and products. So if this one is high, that means your reactants are at a higher concentration, which means I would draw my arrow for reverse longer because reverse is favored. But if it's if K is high, products. If K is high, then that means you have a high number over a low number, which means your products are at a higher concentration than your reactants at equilibrium, which means the forward reaction was favored because your reactants are mostly being converted to products. I hope that makes sense. Only the concentrations of substances that can actually change are included in K. So again, this means pure solids and liquids are left out because you can't change their concentration. So in general, the equilibrium constant, which is labeled K, this is a capital K, by the way, excuse me, which I want to distinguish between the lowercase k is just a generic constant, whereas capital K is the equilibrium constant. There are going to be several versions of K. I already went over Kw, which is the ionization constant of water at equilibrium between water dissociating to form hydronium and hydroxide, and hydronium and hydroxide reacting to reform water. So it is, in words, the ratio of the mathematical product of the concentrations of the products at equilibrium to the mathematical products of the concentrations of reactants. In other words, the concentration of the products over the concentration of the reactants. That's K. And this whole thing is called the equilibrium expression. Each concentration raised to the power of the coefficient, so make sure you start with a balanced equation. So let's look at an example, the same example that we looked at in the last chapter for reaction mechanism. If we look at the reaction between hydrogen and iodine gas in a sealed flask at an elevated temperature. Now we can we can observe this because iodine has a very purple color. So the rate of reaction is followed by observing the rate at which the violet color of iodine vapor lessens, because when decreases. When you first put them in, you have hydrogen gas, which is colorless, iodine gas, which is very, very deep purple, and hydrogen iodide gas, HI, is also colorless. So when you first mix them together, as H2 and I2 react, you're going to see the color start to fade as the iodine gas is used up to form colorless HI, but then you'll reach a point where the color stays the same. So you'll see the color decrease as the iodine concentration decreases. But then when you reach equilibrium, the color will remain the same because the concentration of iodine doesn't change anymore. So that's when you first start the reaction. You can see how it's slightly less purple. And then finally you reach a stable color. Then you know equilibrium has been reached. Suppose the hydrogen gas is present in excess and the reaction continues until all of the iodine is used up. The color from the iodine gradually disappears because the product, HI, and the hydrogen gas are both colorless. So again, as iodine is used up and it forms the colorless hydrogen iodide, that purple color will fade. In reality, the color fades to a constant intensity, but it doesn't disappear completely because the reaction is reversible. The HI is going to decompose to reform hydrogen and iodine. So in a reaction that goes to completion, we got two there. There's a gas. So this is clear, this is purple, and this is clear. Okay, so if it were to proceed to completion, then you would see the purple disappear, it would get less, it would decrease until it finally disappears completely. But that doesn't happen because it's reversible. So there comes a point where the color will remain constant. So the rate of the reverse reaction will increase as the concentration of hydrogen iodide increases, and eventually you will reach equilibrium. Okay. So a constant color indicates that equilibrium exists, and that's your net chemical equation. So from this chemical equation, we know that it's balanced because we have our coefficients in place. We can write the chemical equilibrium expression. So it's K equals the concentration of hydrogen iodide squared over the concentration of hydrogen times the concentration of iodine gas. So let's look at an example problem. An equilibrium mixture of N2, O2, and NO gases at 1500 K is determined to consist of 6.4 times 10 to the minus 3 moles per liter of nitrogen, 1.7 times 10 to the minus 3 moles per liter of oxygen, and 1.1 times 10 to the minus 5 moles per liter of nitrogen monoxide. What is the equilibrium constant for the system at this temperature? So we analyze what we're given and what we're asked to find. We're given the concentration in molarity of nitrogen gas, oxygen gas, and nitrogen monoxide. They've asked us to calculate K. So our plan is to write a balanced chemical equation first. So we do that. We've got N2 plus O2 yields 2NO, and it's reversible. And then from this, we write our chemical equilibrium expression. So we get K is equal to NO squared over N2 times O2. And we were given each of these in the original question. So all we do is plug those numbers in and use our calculator to calculate K. We cancel all of our units. So K has no unit. You see that you've got moles per liter squared divided by moles per liter times moles per liter. So everything cancels. And you get 1.1 times 10 minus 5. All right. I'll go through one and then I'll have you guys go through one. At equilibrium, a mixture of N2, H2, and NH3 gas at 500 degrees C is determined to consist of 0.602 molar N2, 0.42 molar H2, and 0.113 molar NH3. What is the equilibrium constant for the reaction? Now, they've already given the balanced equation. So all we have to do is write our equilibrium expression. So we get K equals NH3 squared over N2 times H2 cubed. So I'm going to replace that with the values we were given in the question. So NH3 is 0.113. That's squared. And nitrogen is 0.602. And that's not any exponent. And H2, where's that? 0.420 cubed. Get out my calculator. 0.113 squared divided by 0.602 times 0.42 cubed. There we go. Put my bracket in the wrong place. And I get 0.29. Is that right? Yeah, 286. Easy peasy, right? Hey. All right, you guys try this one. I'll just put here AC. So the reaction AB2C yields B2 plus AC reached equilibrium at 900 K in a 5-liter vessel. At equilibrium, 0.084 moles of AB2C, 0.035 moles of B2, and 0.059 moles of AC were detected. What is the equilibrium constant? So here, you have to do one extra step, excuse me, because I haven't given you the concentration in molar, but I have given you the amount of moles and I have given you the volume of the container. So the first thing you want to do is convert all of these to concentration in molarity. So you've got moles per liter. So 0.84 over 5. And that's going to be the molarity for AB2C. We've got 0.035 over 5 liters is going to be molarity for B2. And 0.059 over 5 is your molarity for AC. 0.084 divided by 5. That's 0.0168. And was it 0.035 divided by 5? That's 7 times 10 minus 3. And 0.059, 0.0118. Okay, so those are the concentrations you use. So you got K is equal to B2, and everything's already balanced, times AC over AB2C. And my B2 is 7 times 10 minus 3. AC 0.118 and 0.0168 for AB2C. So in the calculator, 7 times 10 minus 3 times point. Oops, sorry, so 0.118. Make sure you copy your numbers right, not like I did. Oh, 7 times 10 minus 3 times 0.0118. I just pushed clear instead of divided by. Bruh. 7 times 10 minus 3 times 0.0118 divided by 0.0168. You should get 4.92 times 10 power minus 3. Now, I'm not bothering with units at all in my equilibrium expression because I know that K does not have a unit. So what's the point? Yeah, 4.9 times 10 minus 3. Turtle. Wait.